Good morning all, my name is Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today I am discussing about noise in color images. So, images or noise is there. We are occurring including the noise is there. Maybe the noise will be occur in the original images. But image noise is random variation of brightness or color information in images and is usually an aspect of electronic noise. It can be produced by the images, sensor and circuitry of a scanner or digital camera. Image noise can also be originate in film grain and in the unavoidable short noise of an ideal photon detector. So, suppose one photo camera or in the form of it is we are calling as a sensor. Sensor is capturing one picture. So that is a analog. When we are converting from analog to digital, maybe the noise will be occur. So this noise, especially we are discussing about in color images. So how much? What is a noise? What is a type of noise? So if we know the type of noise, then we have to use the type if the related filters. Suppose if I know the noise type, then we know type of filter. To reduce noise. So first we have to identify the which type of noise. Then only we have to use type of filter. Regarding depends on the noise, we have to use the filter type of that filter. Then we are reducing the noise. Okay. So noise is common thing, but which type of noise is occurred? That is the important role. So image noise in random variation of brightness or color information in images and is usually an aspect of electronic noise. It can be produced by the image sensor and the circuitry of a scanner or digital camera. Image can also be originate in film grain. Okay, most of the film industries are in any film grain and the unavoidable short noise of an ideal photon detector. Okay, maybe it is a short noise. So the same characteristics in each color channel possible for color channel to be affected differently by noise. Different noise levels caused by differences in the relative strength of illumination available to each of the color channels. For example, if we are taking what is a type of filter, so I'm taking here a red filter. So when it is a CCD camera, so CCD sensors are noiser and lower levels of illumination red component tend to be noiser than two components in following slides. We take a look at noise in color image and how noise carries over when converting color model. So noise is occurred then filters are needed to remove noise. So if noise is occurred, how can you find out noise is occurred or not? Suppose sometimes short noise will be occur. So depends on your noise, we have to use the type of filters are there. Suppose in the same characteristics in each color channel, possible for color channel to be affected differently by noise, different noise levels caused by the differences in the relative strength of illumination available to each of the color channels. Suppose CCD camera, CCD sensors are noiser at lower levels of illumination, red component attend to be noiser than two components are in the following slides. But we have to take a look at noise in color image and how noise carries over when converting color model. So the hue and saturation components are degraded due to the nonlinearity of the COS and min operations. The intensity image is the average of the RGB images. So we are talking about noise in color. Noise in color images. So what are the color images? The images in the form of red, green, and blue. When the images are in the form of red, green, blue, then only we are calling as these are the color images. But noise is there. So how we are finding out? Hue, saturation and intensity. Hue, saturation and intensity are the major things to finding out the what is the color type are there. So hue and saturation and intensity are the degraded due to the non-linearity of the COs and means operations. So when I'm taking the color image, that image in the intensity image is the average of RGB images. So what are the intensities of RGB? So what we have to find out the intensity values. So if these intensities are changed, then noise occurred. So what we have to do? What are the original intensity values are there? We have to change that original intensity values with the help of mask or with the help of mask or with the help of filters. Then only we are changing the noise levels. So the hue and saturation components are degraded due to the non-linearity of the COs and mean operations. So the intensity images is the average of the RGB images. So if the noise is occurred, then what will happen? Filters are used to remove the noise. So suppose here I am taking one example. It is the input image with noise is there. So RGB image with the green plane occurred by salt and pepper noise. Okay. So input image with the noise is occurred. So what type of noise is there? Clearly they are telling that here it is a RGB. The color is a RGB with salt and pepper noise. With the salt and pepper noise is there. Next, what we have to do in the figure B? Hue components of HSI images. Already we know that we have the hue, saturation and intensity. We have to find out these three in the color images. I'm talking about hue, saturation and intensity or in color images. So the color image in the form of red, green and blue. So when the color image in the form of red, green, blue, then we have to go for the hue, saturation and intensity values to finding out the type of noise, and we are finding out the which type of filter is suitable to remove the noise. That is an important thing. So in the figure B, we are taking hue component of HSI image. Okay, HSI means hue, saturation and intensity. Hue, saturation and intensity. So hue components of HSI image. Especially I am taking hue here. Especially I am taking hue. Next to figure C, I am taking especially saturation component. Figure D I am taking intensity. So it is the hue, saturation and intensity in gray level. So the color image, the figure A is a color image with the noise is there. Which type of noise means salt and pepper noise is occurred. So how we are removing? First we have to converting into in the form of hue, in the form of saturation, in the form of intensity. Then only we are using the which type of filter is suitable to removing the noise. That is a process. Here another one is there. Figure A, figure B and figure C, figure D. So figure A to C, that is a red, green and blue. Red, green, blue. So RGB is there in the component of images corrected by additive Gaussian noise of mean 0 and variance is 800. So what is that means here? Output RGB image. So figure A to C, what is happened means A to C, red, green and blue component of there, but it is corrected with additive Gaussian noise. Additive Gaussian noise is occurred. So how many types of noises we will discuss later, but it is some example for our idea purpose. We are taking some examples of this one. So figure A, B, C are the red, green, blue of the original color images, but what has happened means it was corrupted with additive Gaussian noise is there. That is mean is 0 and variance is 800. But what is output? The color output is a color image that is in the form of RGB. But what will happen means I used filters to remove additive Gaussian noise. That is the output image with RGB color. So noise in images. Image noise is random variation of brightness or color information in the images captured. It is degradation in image signal caused by external sources. Images containing multicative noise have the characteristics that the brighter the area of the noise it is there, but mostly it is additive. We can model a noisy image as. So noise images are there. How can you find out the image is a noisy? How we know? So if the noise is there, that is a random variation of the brightness or color information in the image captured. So the brightness or color should be changed if the noise is occurred. Then it is a degradation in image signal caused by external sources. Image containing multicative noise have the characteristics that the brighter the area, the noisier it, but mostly it is additive. We can model a noisy image as capital A of x comma y equal to capital H of x comma y plus B of x comma y, where A of x comma y is the function of noisy image, H of x comma y equal to function of image noise, B of x comma y is equal to function of original image. Okay, it is the equation for noisy image. So A of x comma y equal to H of x comma y plus B of x comma y. So A of x comma y is the function of noisy image. So noisy is equal to H of x comma y equal to function of image noise, function of original image. Okay, so noisy image with original image. How much noise is there? What is the percentage of noise? Okay, that will be depending on your noise image plus original image. Okay, here I am taking one example: addition of random noise in an image. Okay, it is the original input image. So what has happened means here some noises occurred, some dots are there, some white color whitish dots will be there. So it is one type of noise is there. It is the original image, but figure B is a noises occurred. So I have to find out which type of noises occurred. Then I have to using the which type of filter is suitable for this one. Then only I will remove that one. But here, what is the thing means which type of noises happened. Okay, that is the thing. It is the addition of random noise. Addition of random noise in an image. Why? Because dots are there. That was captured in the original image, and the color also brightness is changed. Here the face is the some white color is there, but here some bright blackish color is highlighted. So here background some gray color is there. Here black color is there. So the color will be changed. In the previously we discussed here. If the brightness or color will be changed when the noise is occurred. Here also the brightness is changed. The whitish is converted to the black and black is converted to the white like this. And dot lines also occurred. So it is called a noise. But which type of noise means? It is a random noise. So sources of image noise. While image being sent electronically from one place to another. So one device to another we are converting the image. Then what will happen? Maybe the noise or maybe the clarity of the original image will be changed. Sensor heat while clicking of an image with varying ISO factor which varies with the capacity of camera to absorb the light. Types of images noise. When I'm using the camera, okay, so capturing the person. So this camera maybe light is high. So this light is focused on the person. Okay, maybe the person original image will be changed. Why? Because of the light is applied to the that person with the sensors. Okay, with the sensor. So while clicking of image with varying ISO factor, which varies with the capacity of camera to absorb the light. So types of image noise. There are different types of image noises. They can typically be divided into three types. So noise is there, but how many types of noises there? How can we identify the types? So there are three types of noises are there. So majorly we are talking about the noise. These noises are dividing as a three types. First one is a photo electronic, second one is a impulse, third one is a structured. So already here we discussed electronically from the place to another. Second one is a sensors. Okay, so noises are divided into three types: photo electronic, second one impulse, third one is a structured. So in the photo electronic there are two types are there: photon and thermal. Photon and thermal. And impulse noises are two types: salt noise, pepper noise. Okay, so structured is only one type is there. So it is a classification of noise. So noises are three types: photo electronic, impulse, and structured. In the photo electronic, two types: photon and thermal. Impulse noises are two types: salt noise and pepper noise. Sometimes we are calling as a salt and pepper also. Salt and pepper noise. Okay, each one we'll discuss later. Another important types of noises are there, that is a typical noise models. So these are about noise models. Previously we discussed classification of noise. Okay, so noise models: uniform noise, Gaussian noise, salt and pepper noise, gamma noise, and relic distribution noise. Okay, so uniform noise, Gaussian noise, salt and pepper noise, gamma noise, relic distribution noise. So these type of five types we will discuss. So these are about the typical noise models. And it is a summary of noise models. So which type of noise is there? First we have to find out type of noise. Then we have to find out what are the parameters for the noise and what is the formulation for the noise. Okay. Suppose I am taking here noise type, first one, and the formulation parameters. What are the parameters for the noise? First one, noise type. First one is a photon short noise. That is a NP, photon short noise, NP. And what is the formula means? Poisson distribution. I plus NP is equal to the P of I. So that is a Poisson distribution, P of I. NP is the, what is that means? Noise of the photon. Okay. I plus NP means original image with noise. I plus NP. It is equal to the Poisson distribution. So what are the parameters means? It is the system gain of K. And another one is a read noise. So read noise means end read. Read noise means end read. So it is a Taki lambda distribution. End read equal to TL, Taki lambda distribution. So what is the means shape means? It is the shape is a lambda I am taking. What are the color base means? Mu C. Scale equal to sigma TL. So it is the noise type. That is a read noise. Another one is a row noise. So row noise is a NR. So Gaussian distribution NR equal to N of 0, sigma R. What is the scale means? Sigma R. So quantization noise, that is a NQ. Quantization noise NQ. It is a uniform distribution. NQ equal to U of 1 minus 1 by 2Q, 1 by 2Q. Minus 1 by 2Q, 1 by 2Q. So what are the parameters means? There is no parameters. So here I am taking one example of 4 types of noises are taking. So noise type 1, photon short noise, read noise, and row noise, and quantization noise. So photon short noise is a Poisson distribution. What are the parameters means? System gain with K. Read noise is a Taki lambda distribution, and what is the shape is a lambda. Color base is a mu C, and what is the scale for that image is a sigma TL. And row noise is there. That is a Gaussian distribution NR, and what is the scale means? Sigma R. And the quantization noise is a NQ. So what are the formulation is a uniform distribution. So that is a number. So we discussed here uniform distribution, Gaussian, salt and pepper, gamma, relic. So all those things here we can observe Poisson, Gaussian uniform noises. So these are the noise models are there and with parameters. So first type Gaussian noise. So in the noise models, first noise model is a Gaussian noise. Gaussian noise is a statistical noise having a probability density function equal to normal distribution, also known as Gaussian distribution. So random Gaussian function is added to image function to generate this noise. It is also called electronic noise because it is arises in amplifiers or detectors. Suppose what are the sources are means thermal vibration of atoms and the discrete nature of radiation of warm object. Suppose one person is there, I have to capture the person with a camera. So camera we are calling as a sensor. Okay, when the camera problem or sensor is a problem. So what problem? If the camera is a problem or sensor is a problem, that will affect to the object. That will affect to the object. Like these noises are called Gaussian noise. Okay, it is not a problem of person or object. It is a problem of sensors or physical devices. So Gaussian noise is a statistical noise having probability density function equal to normal distribution, also known as Gaussian distribution. But a random Gaussian function is added to image function to generate this noise. It is also called as a electronic noise. So here a good example is a sensor. It is an electronic noise because it arises in amplifiers or detectors. Okay, we are finding out the detectors to object, finding the object. So what are the sources means thermal vibration of atoms and the discrete nature of radiation of warm objects. So it is one example of plot of probability distribution function. So PDF, probability distribution function. Okay, here I am taking the mean values. So here one waveform or one image with the mean. So when I am taking the middle point is a mean equal to 0, lowest values are minus 1 and the least values of positive side is a plus 1. It is a positive and a minus. So when on the negative side it is a minus 1, positive side it is a plus 1. Okay, the side image is a bell-shaped probability distribution function which have mean equal to 0 and standard deviation sigma equal to 1. So when I am taking this one 0 to 1, mean equal to 0, sigma value equal to 1. So it is from 0 to 1. The distribution function PDF equal to 0 to 1 function, that is a mean. So another one is a impulse noise. So impulse function in the discrete world, impulse function on a value of 1 at a single location and it continues world impulse function is idealized function having unit area. So suppose I am taking impulse function in discrete world and a continuous world. So it is a discrete function. So from 1 here 1 to 1, if I am taking it is 1 to 1. It is a continuous function, means continuously there is no change, directly increasing from 1. So it is in 0 to 1. So directly it is a continuous function, but it is a discrete function like this. Dotted lines are discrete. So it is called impulse noise. And types of impulse noise. In these noises, what are the types of impulse noises are there? There are 3 types of impulse noises are there. Salt noise, pepper noise, salt and pepper noise. Salt, pepper, salt and pepper noise. These are under impulse noises are there. So what is the salt noise? Salt noise is added to an image by addition of random brightness with 255 pixel value over the image. So 255 is nothing but it is the highest value, highest brightness of the picture. That is the 255. But the brightness is very high, very high. So what we have to do? We have to reduce the noise. So when the picture value is highest pixel value or highest brightness value, that is a salt noise. And pepper noise. Salt noise is added to image by additive dark with 0 pixels. Okay, highest value is a salt, lowest value is a pepper. Okay, the intensity is 0. Salt and pepper noise means it is maybe a 0 or maybe a 255. Salt and pepper noise is added to an image by addition of both random or bright with 255 pixel value and random dark with 0 pixel value all over the image. This model is known as a data drop noise because the statistical is drop of the original data value. So suppose I am taking one 3 by 3 matrix I am taking here. So in this 3 by 3 I am taking some intensity values are 255. Some intensity values are 255. So some intensity values are 128. Here zeros are there. Here 86. Some 95. 101. So 91. 76. 34 like this. So some are 255 are there. Some of 0 is there. It is the most brightness. Brightness is very high. Brightness is nothing means 0. If the brightness is high means I am considering as it is a white. 0 means I am considering as it is a black. It is when the completely black or completely white. So when I am taking this 255, I am taking it is a salt noise. When it is completely 0 means that is a pepper noise. So when I am calling salt and pepper means the intensity values are between the 0 to 255. Completely change it to 0 or completely change it to 255. That is the salt and pepper noise. So salt and pepper noise is added to an image by addition of both random bright with 255 pixel value and random dark with 0 pixel value. Maybe a 0 or maybe a 255. 0 or 255. The variation is between that 0 to 255. This model is known as a data drop noise or statistical drop noise or salt and pepper noise. And another one is a poison noise. The appearance of this noise is seen due to the statistical nature of the electromagnetic waves such as X-rays, visible lights and gamma rays. Then if I am taking X-rays or gamma rays of the sources emitted number of photons per unit time, these rays are injected in patient's body from its source in medical X-rays and gamma rays in image system. These sources are having random fluctuation of photons. Result gathered images of has spatial and temporal randomness. This noise is also called quantum or photon noise or short noise. In the first beginning we have discussed short noise or photon noise or gamma noise. These are under poison noise. Okay. So medical X-rays, where the medical X-rays. Gamma rays, photons. So these are under medical. So these are the poison noises. So this noise is occurred statistical nature of the electromagnetic waves such as X-ray, visible light and gamma rays. So these are completely hospital or medical images. So X-ray and gamma ray source emitted number of photons per unit time. These rays are injected in patient's body from its source in medical X-rays and gamma rays imaging system. These sources are having random fluctuation of photons. Result gathered image has spatial and temporal randomness. This noise is also called quantum or photon noise in short noise. These are about the noises and the references. So here we discussed definition of noise. It is a random variation of brightness or color information. So noise is or color image. So when the noise is random brightness or color information in an image, usually aspect of electronic noise. It can be produced by the sensor and the circuitry of a scanner or digital camera. It is nothing but a physical device. So this noise can be originate in film grain and in the unavoidable short noise. Okay, short noise is nothing but a poison noise. Ideal photon detector. So the same characteristics are occurred in the color channel of possible of color channels in the affected by different possible types of noises. So when we are taking the noisy image in the color, that is the red, green, blue in the image form, and we have to finding out the intensity values of the color image, and we have to take the hue value and saturation value and intensity values to finding out the noise of the image. So here we are taking the hue value, saturation value and intensity values to finding out the noise in the original image. Here also I am taking the original image, we are converting to the red, green, blue and converting to the noiseless image. So noise in images. So it is the original image and it is a blurred image, and with the colors are changed, brightness is changed and dotted lines are occurred. Then it is called the random noise. So what are the sources of image noises? Maybe the physical devices. It will be occurred with the physical devices. That is the sensors or types of noises. So noises are three types: photoelectronic, impulse, structured. In the photoelectronic, photon and thermal. In the impulse noise, salt noise and pepper noise. So what are the models of noises? Means uniform noise, Gaussian noise, salt and pepper noise, gamma noise, Rayleigh distribution noise. So it is a types noise type, formulation and parameters. First one is a photon shot noise, read noise, row noise and quantization noise with suitable parameters. So it is a Gaussian noise, it is a physical device. It will happening with physical devices. So if what is the range means probability density function is a 0 to 1. It is a mean value. So impulse noise. Impulse noise means if directly or indirectly changing the values or mean values. So impulse noises are three types: salt noise, pepper noise, salt and pepper noise. When the brightness is very high, that is the intensity values are 255. So if the intensity values are 0, then is a pepper. If the intensity values are changing between 0 to 255, that is the salt and pepper noise. Okay. Poison noise means it is the medical images, medical field, or X-rays, gamma rays, visible light, and short noises, photons. These are the gamma noises or poison noises. It is about the noises, types of noises. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.